In this unit, we are going to take a look at statistics. The study of statistics is taking data and doing certain statistical calculations or using certain statistical structures such as graphs, like histograms and frequency polygons, two of the things we're looking at today, to help us make decisions about data. Your project that you're going to be doing starting next week, which I believe, if everything stays the same, which let's face it, probably won't, I'm hoping to give you up to 5 class periods to work on it prior to Christmas, including 3 next week. In that project, what you're going to be doing is you're going to try and answer a question. It's going to be a question that is interesting to you, but it should also be a question to which you don't know the answer. We'll talk more about that next week, but a sample question could be, well, tell me something you're interested in, Malcolm, outside of school, something, a hobby of yours. Drawing. So art? Okay. One of the things that you might ask is, who's the most successful artist of all time? Now, the thing is that there's lots of different ways to measure things. For example, if I was to say, pose this question, and I'm doing this somewhat tongue-in-cheek, but suppose the question was, who's the best teacher at our school? Okay, how would you measure it? Would you measure it by someone's age? Would you measure it by someone's years of experience? Would you measure it by how many people pass their class? Would you measure it by the class averages in their class? Many different ways that you could measure, some of which would be better measuring tools than others. If I was to measure who my favorite student was, I could look at their mark. But when we think about that, does somebody's mark tell you what kind of person they are? No, it just tells you how they perform academically. So statistics help tell part of the story. And when you want to answer a question, it's your job to pick statistics that are relevant to the question you're trying to answer. So if you want to figure out who the greatest hockey player is currently, you can look at many different measures. All right. So to start off today's lesson, we want to take a look at a quick little exploration or an explore question. Margaret inherits her grandfather's coin collection. How can she organize the catalog of coins to see how many of each type that he has? Well, what do you think? Got a bunch of coins. How can you organize them? Groups according to what? Value's a nice idea, except what I would say to that is what we have in Canada is nickels, dimes, quarters. If you go to like Mexico, they probably don't have nickels, dimes, quarters. I could think of 2 different ways to organize it. Type, so type meaning what? Where it came from, that would be number 1. That'd be number 1. What else does it say or indicate on coin that we could catalog it by? The date. We could look at where it's from and the date. All right? We could do it that way. We could do it either way, or we could do it both ways together. And the sample answer, oopsies. Sample answer is by year, or she can go by face value. I said the problem with that is those you don't know if they have the same value in every country, or they can go by condition, or they can go by where they're from. Either way, you can organize the coins in a variety of different ways. Okay? So, the Red River has a variety of problems. And those problems are when there's too much precipitation, and if there's too much precipitation, there may be a flood. 4 notable floods in the 20th century were 1950, 1979, 1996, and the year 1997. The flood in 1997 was known as the flood of the century in Manitoba and in North Dakota. From 1950 to 1999, here are the flow rates at the Redwood Bridge of Winnipeg, Manitoba, all the way from 1950 to 1999. So clearly, if we look at years 1953, 1954, those are pretty low flow rates. The highlighted years, 50, 79, 96, 97, those are massive flow rates where all of them are over 3,000. In fact, 1997 is over 4,000. It's over 4,000. Okay? So the question here is how can we come up with a number that, like a cutoff, whereas if it's over this number, there's serious flooding. If it's under that number, it's not so serious flooding. So we're going to look at 3 different ways. And the title of today's lesson is about looking at frequency distributions, histogram, and frequency polygons. And we're going to look at what each one of these would look like for this problem. Okay? So for the frequency distribution, we look at the highest and the lowest numbers because we have to know where we're starting and where we're going up to. So the range is the difference between the highest and the lowest, and that's over 4,000. What we have to do is we have to come up with intervals. In other words, we have to go from like 0 to 500, 500 to 1,000, 1,000 to 1,500, and so on and so on. We could also go 0 to 400, 400 to 800, 800 to 1,200, 12 to 1,600, and so on and so on. But one thing is true. We need to make sure that these intervals are of equal length. So if each interval is 400, cool. If each interval is 500, cool. That's fine. All right. So that range is 4428. Here's a very important thing that you might want to highlight or keep in mind. Most tables have between 5 and 12 intervals. Most tables have between 5 and 12 intervals. So in other words, you should divide the range always by a number between 5 and 12. Okay? They use 10, and when you divide it by 10, you get 442.8. So that means that the interval has to be, if you want 10 intervals, the interval has to be at least 442 wide. You're not going to go 442 wide. That's a stupid number to go up by because it's just, silly. You want to pick a nice even number. You could go up by 450 if you're so inclined. but 500 is even better. So that's why they go up by 500. So every one is going to be a multiple of 500. All right, that's an easy to work with number to work with. So the intervals go from 0 to 500, 500 to 1,000, 1,000 to 1,500, all the way up to 40, all the way up to 5,000 rather. So that makes sure that we have all of the numbers accounted for. And then what you need to do, so you need to create, if you're going to do a frequency distribution table, you have to make all of these intervals, Malcolm. You have to count how many times do you get a number between 500 and 1,000 and tally them up. And of course, there's 11 tallies here, which is why the number 11 is right next door. Okay? And this basically gives you an idea of where the concentration of the numbers is. Okay? Now, this is an interesting thing because I would ask you this question, and this is always will come up at some point. What if you get exactly 500? Does it go in here or does it go in here? Well, each interval begins just after the first value. So in other words, this goes up to exactly 500. This is anything above 500 up to 1,000. Anything above 1,000 up to 1,500. Anything above 1,500 up to 2,000. So that way you can't count a number twice. If you get exactly 500, exactly 3,500, there's only one place that number's going. So what can we see here? We see that 17 of the 50 years had a water flow less than or equal to 1,000. So we're gonna say that there's no flooding anytime it's less than 1,000. Also from the data, the flood of the century had a flow rate of 4587 meters cubed per second. And this number was significantly higher than all the other numbers in the table. Also, we knew that there's 9 floods, and 4 of them were called severe floods. Since the floods in 4 years when the flow rates were 3,000, we call those severe, then that's the number that we could kind of grab onto. So what we could say then is that maybe the minimum flow rate that results in a flood should be somewhere between 2,000 and 2,500. That could be the absolute minimum number that might cause a flood to occur. Okay? You can check your prediction by comparing the years that had flow rates from 2,000 to 3,000 with the historical records of flooding. So you can actually look it up and see if there was floods in those years. Okay, but basically, this is how we can use a frequency distribution table to organize the numbers. Because if we're just looking at like 50 numbers, it's kind of overwhelming. So if we organize those 50 numbers into this table, it helps us get an idea of where all the numbers sit. Okay? So exact same problem. Now make a frequency distribution by using a histogram. So to make a histogram, we actually, well, the histogram is, interestingly enough, they created a different, their intervals here are different than the ones that we just looked at. As I said, you could go up by 450, right? Well, that's what they do. They start at 150, they go up by 450, and they go all the way, and they tally in the appropriate spot for each interval. So this is just basically a slightly different version of what we saw before. So if Sky and Malcolm, if I gave you a bunch of data, maybe I gave you, I don't know, kids' marks and kids' averages in the school, you would probably want to make something like this to kind of organize it. And maybe, Malcolm, you might go up by 10s. Maybe Sky, you'd go up by 8s for your interval. You'd have two slightly different frequency distribution tables. Does that mean that Malcolm's right and Sky's wrong, or Sky's right and Malcolm's wrong? No. Okay? You can make your intervals as wide as you want, but remember, you should have between 5 and 12 intervals. And if you have between 5 and 12 intervals, then you're fine. Okay? So using their frequency distribution table, they create a histogram. This is a histogram. When we take a look at the histogram, what kind of graph does it look like? Looks like a bar graph. Now there's some differences between a histogram and a bar graph. Let me tell you what those differences are. Number one, in a true histogram, the bars touch, always. If there's a bar, right? If there's a bar. Like we see that there's this blank spot between 3300 and 4200. There's no bar there because there's nothing there. But anywhere there's data, the bars are touching. Here's also the way histogram works. What this says is from 150 to 600, there are 11 years that had flow rates between 150 and 1600. 150 and 600, not 1150 and 1600, but between 150 and 600, there was 11 years with flow rates between those two. Between 1500 and 1950, there was 12 years in that range. And between 4200 and 4650, there was only 1. So to make your histogram, obviously it is like a bar graph. You do need to label your axes, water flow in meters cubed per second, number of years. But in order to put the numbers properly, the numbers along the horizontal axis are the first number in the interval. 150 is the first number in the interval. Then 600, then 1050, then 1500. And if we look back at the frequency distribution table, we see it just goes along like that. So using the first number in the interval to help you make the numbers here. And of course, you will put the last number here as well. Okay, so that's how you make a histogram. The bars have to be together. So the conclusions that can be drawn here is that with the exception of 1500 to 1950, the frequency goes down. So basically, lower flow rates tend to be more common than higher flow rates, because the higher the bar means it happens more frequently. Okay? So the conclusion we can draw is that a year with a lower flow rate is more common than a year with a higher flow rate. So, again, knowing that there's 9 floods, based on the histogram, the flow rate was bigger than 1950 in only 12 years. these 12 years have to include those 9 flood years. So based on 9 being pretty close to 12, the conclusion that's made here is that floods occur when the flow rate is greater than 1950. Now remember when we looked at just the frequency distribution table before, what they said the cutoff was 2000. So this person, using slightly different intervals and looking at a histogram, looks at it with a slightly different lens. Okay? All right. Now, what if we look at a frequency polygon? So what is a frequency polygon? Well, this frequency table is the exact same as the one we just looked at, except there's one difference. This midpoint. What the heck's the midpoint? The midpoint is the halfway point of the interval. So if we're going from 150 to 600, the midpoint is the halfway point in that interval. So why is that important? Well, because we're going to label the midpoint on the frequency polygon. So when we look at the frequency polygon, these numbers down here correspond to the midpoints of the interval. So when we make a frequency polygon, the numbers on the bottom should be your midpoints. Going vertically, the numbers still represent the frequency. And when we talk about the frequency, we're talking about the frequency of that interval. So for example, 1725 has a frequency of 12. That means that in that interval of where 1725 lives, there's 12 occurrences. Okay? So a frequency polygon is almost identical to a histogram, except we're using points and we're connecting the points, and the numbers down here are the midpoints rather than the beginning points of the interval. So most of the data is in the first 4 intervals, and the most common flow rates between 1500 and 2000 meters cubed per second. After this, the frequencies go down. There were 6 years where the flow rate was around 2625, 3075, or 4425. So these must have been the flood years. The other 3 floods should have occurred when the flow rate was about 2175. According to the frequency polygon, there were flows around that midpoint in 6 years. Assuming that the flow rate in 3 of those years was 2175 or greater, then floods should occur when the flow rate is somewhere around 2175 or greater. So this time, because we're using the midpoints, of course, we're going to get slightly different numbers than by using the endpoints of the interval. But whether we look at the frequency distribution table, which we looked at to begin with, the histogram, or the frequency polygon, we all see kind of the same information. We just see it a slightly different way. Okay? So part A, identify similarities and differences in the frequency distributions that Francine, Tasha, and Monique create. So what can we say about them? Well, they all involve the same data. All that data is grouped into intervals, although the intervals are a little bit different. The first interval is just a table. The last 2 intervals are graphs. And the last 2 also use the exact same interval width of 450. What are some differences? Well, one used a table, the other two used graphs. And the first one used an interval width of 500, where the last two used an interval width of 450. Part B, Francine used a different interval width. How did that affect the distribution of the data? Well, it just lands in different intervals. Nothing too complicated about that. So suppose Francine created a frequency distribution using an interval width of 200. Do you think this interval would make it easier to see which water flow rates result in flooding? Why or why not? Well, given that the data was spread out over 4,400, if you divide it by 200, you'd be looking at 22 or 20, you'd be looking at about 22 intervals. 23 intervals, actually. That's a lot. So that really wouldn't tell you a whole lot, because probably in most of them, there'd only be one number, or zero numbers, or maybe two numbers. It'd be a lot harder to distinguish where the frequencies were. So 200 would be a terrible interval width, because there'd be too many, there wouldn't be enough data to put in each interval. And part D, would 2000 be a good interval width? Would no, because there'd only be three intervals, so it'd be really hard to tell apart those three intervals. Okay? We want anywhere between 5 and 12 intervals, and those intervals have to be of the same width. Now, like I said earlier, when we talk about statistics, we're taking information, we're doing mathematical calculations, and we're making mathematical decisions based on those calculations. I could look at the same data and make different observations. What do I mean by that? Well, let's say, I'm going to make something up here. Let's say I had a class and the marks were 95, 90, 52, 10, 8, and 5. Those are the marks in the class. Totally fictitious. Okay? I could look at those numbers and say, hey, look, I got 2 students in the 90s. This is one of the best classes I've ever had. A third of my classes has A pluses. You could also say, well, half your class is 10% or less. That's the worst class you've ever had. Truth be told, neither of those statements is probably true. But my point being is that we can take data. I don't want to say we can take data and make it say anything we want, but data can be interpreted in many different ways. Okay? Data can be interpreted in many different ways. And there's a whole lot of different types of statistical calculations or tests. Chances are you're going to have to do more than one of those calculations or more than one of those tests in order to figure out what your answer is. Okay? Or you're going to have to look at more than one set of data. So another example. Comparing data looking at histograms. We're looking at earthquakes in 2005, 2006, 2007, 2008, and 2009. Which of these years would have had the most damage from earthquakes? Understanding that the higher the magnitude on the Richter scale, the more massive the earthquake. You say 2005. Okay, why? Okay. What says you, Malcolm? (2007). Why? There's what? There's 3 between 5 and 6. Okay. When I was looking at this, I thought maybe 2008, because there's 16 earthquakes between 4 and 5. And if you look at between 5 and 7, there's 9 of them. Like I said, when we look at data, depending on what lens we pick to look at the data, we can make different decisions. Does that mean that you can justify everything? No. Some things will have a stronger argument, okay? Some things will have a stronger argument. So, there's some information on the Richter scale. If you have an earthquake between 3 and 3.9, it feels like a passing truck, not much damage. 4 and 4.9, it's felt by almost everybody. There's a movement of unstable objects. 5 and 5.9 is felt by all, considerable damage to weak buildings. 6 to 6.9 is difficult to stand. Ordinary buildings collapse, somewhat. Between 7 and 7.9, people unfortunately usually get damaged big time, and there's a big time destruction of ordinary buildings. And more than 7.9 is a widespread loss of life and destruction. And the Richter scale is a logarithmic scale. So what does that mean? That means that every time you go up 1 on the Richter scale, like say a 5 versus a 6 would be 10 times more powerful than a 5. And a 7 would be 10 times 10 is 100 times more powerful than a 5. Crazy. So the thing is we just looked at those graphs. We didn't really do any kind of calculations. We just did the eyeball test. Let's take a look if we look at a frequency table. If we take a frequency, look at a frequency table, says at first glance seemed like 2005 was the worst year because it had the highest bar. That's what you said. However, an earthquake of magnitude 3 does not cause much damage. Okay, so they knew that some minor damage would occur if an earthquake was between 4 and 4.9. So they decided to examine the frequency of those earthquakes, just 4 and up, from 2005 to 2009. So if we're just looking from 4 and up, or rather 4 to 4.9, 2008 had the worst of those. Now, if we look at between 5, now 2008 had the most of those. Now, 4 of the years had 3 earthquakes from 5 to 5.9, while 2008 had 5 quakes with those magnitudes. So if we look more detail at 2008 and 2009, it looks like 2008 would have the most damage because there's way more of them. Now, lots of them are between the 4 and 4.9 range, but still, there's still far more of them than there are in 2009. So the conclusion could be that 2008 would have the most damage from the quakes. And I believe, Malcolm, you said 2007. And I said 2008. Okay, so it looks like 2008 probably is the most dangerous one. But again, we can look at this lots of different ways and come up with some different responses. Now, Miguel looks at the frequency polygons, makes frequency polygons of these years, looks at 2008 and 2009 in particular, and basically what we see is they have the same frequency, except 2008 is above 2009 as the Richter scale gets higher. So the Richter scale gets higher, around a 4 and higher. 2008 is always ahead of 2009. So based on that, 2008 is the winner. So if you make a frequency polygon for those 2 years, Malcolm, we see that 2008 is a more severe year for earthquakes than 2009. Now, what if we take, I don't really care about the comparing their answers, but I like part B. What other factors should you be considered when determining which year could have had the most damage from earthquakes? What's one way you can measure the damage from earthquakes? Yeah, damages. What else? What's that? Yeah, that would be the same thing, I think. What else? Life loss. Yeah, I mean, it's a terrible thing to talk about, but yeah, how many people passed away? I mean, it's kind of unfair in some ways because if an earthquake happens somewhere like, say, Japan, where people are so congested in Japan, like, there's so many people in such a small space, it'd be a lot different than getting an earthquake, let's say in northern British Columbia. If there's an earthquake in northern British Columbia, there's probably not many people that live around, so there'd be less people that would perish. And damage, yeah, so that's good. So here are some key ideas. I guess just before we go there, you guys are, well, maybe not. No, you are. Well, maybe not. What year were you born, Malcolm? 2000? Oh yeah, you're too young. And Sky, you'd be what? 2000. 1989, the World Series was between the Oakland Athletics and the San Francisco Giants, and the first 2 games were in Oakland. And I was an Oakland fan when I followed baseball more closely. And then they went to San Francisco, and Oakland and San Francisco are across the bay from one another. They're right beside one another. But as they were getting ready to start Game 3, an earthquake happened, and it was one of those massive earthquakes. And I'm sure that some people probably perished in it, but I don't think too many. But it completely ruined the city, at least the part of the parts that were affected by the damage. But actually, there's a really, I mean, if you like sports at all, even if you don't like sports, ESPN has an amazing series called 30 for 30, where they have great documentaries, and some of them are very fascinating. Probably the best of which was the O.J. Simpson one that aired in the summertime. It's 5 parts. Each part was 2 hours, so it's a bit of an investment, but it goes through the whole O.J. Simpson thing. And when I was in high school, when I was in grade 10, that's when he did that infamous thing when his wife and his wife's friend were murdered, and he was being chased by the police, and then his trial and everything. It details the whole thing very very well. But the documentary they did on the 1989 earthquake was interesting because it was a sporting event. They had all the TV broadcasts that were on at the time because of the baseball game, but then they had to go ahead and actually cover an earthquake, which was really, I mean, a whole different thing than a baseball game for sure. But it was really kind of a surreal moment. So moving away from earthquakes and getting back to what we're looking at today, if I give you, let's say we go ahead and we get people to, everybody in the school runs 100 meters, and we want to look at their times to run 100 meters. You don't want to look at 200 numbers. So instead of taking a large set of data, what we can do is we can organize the data into intervals and tabulate the frequency of the intervals. And that's what a frequency distribution is. And we can take a frequency distribution and either leave it as a table, or take that information and make a histogram or a frequency polygon of it. The frequency distribution should have a minimum of 5 intervals and a maximum of 12 intervals. You want the graph or the intervals specifically to show how the data is distributed. You can find the interval width by dividing the range of the data by the number of intervals you want to make, and then rounding to a suitable interval width. The height of each bar in a histogram represents the frequency of the interval it represents. Because individual pieces of data are not visible in a frequency distribution, only the minimum, maximum, and median values are used on those graphs. Okay. Frequency polygons are pretty much the same thing as histograms. However, they are especially helpful when you compare multiple sets of data because they can be graphed on top of one another. And that's what we looked at when we were comparing the earthquakes in 2008, 2009. We took a look at the frequency polygons and we saw which year had the more frequent earthquakes of greater severity. Okay? Okay, so your homework is in your book. I am going to look at the book in a second here. I'll cut this lesson off and I'm going to assign some questions for homework.